All right. Hi, everyone. Thank you for having me, and really excited to present this project to you. So the topic is analysis, design, and construction of the Los Angeles County Museum of Art, or LACMA for short. Like David mentioned, I am at Skidmore, Owings, and Merrill in the New York office, but I used to be in the San Francisco office, hence why I'm on a West Coast project right now, presenting this to you. To give you a little bit of background, so obviously LACMA is located in Los Angeles. The site is right before our project. There's always been like a group of buildings that are associated to LACMA, the museum. In the foreground, you'll see a series of kind of square-shaped buildings. Those are relatively new. And behind that, you see this very organic sweeping shape, and that is the LACMA, the new LACMA gallery that we'll be talking about today. There are some notable features. It spans over this boulevard you can see running diagonally across the screen. That is Wilshire Boulevard, and our building actually straddles two sites on either side of a boulevard, so it has to span 180 feet across that. Not only is there that long span, there's also very long cantilevers, up to 90 feet cantilevers. Just to help orient you on the site, this is the campus plan as of 2006. That's kind of when the discussion of this new gallery building was started. And at that point, those like square buildings that I showed you in the foreground didn't exist yet. So those were opening in 2008, and then we had to demolish some of these buildings on the right side to make room for the new gallery building. The museum board went through a number of iterations with competitions to look for the right architect for this building, and eventually landed on Peter Zumthor from Switzerland. He's very known and respected architect, and a lot of his work is very atmospheric. He's very interested in monolithic forms and concrete forms and materials. And this project, LACMA, would be his first and largest project in the US. So this is a very early, quite early model that he has, and this is a physical model. Everything here is real, like, you can touch it with your hand, like all the trees are actually physically modeled, and this sits in his studio in Switzerland. And you can see also already from very early on, this concept of the organic shape was a very central theme. If you've been to LACMA, you know that there's a tar pit next to the site. That's where, the ancient mammoth, I don't know, I'm not an archaeologist, but there's like bones and stuff in this tar pit. And I think part of the inspiration for the new LACMA was this kind of very organic form. It stems from this tar pit. So there is a strong relationship between the building and the site. Another important design concept for this museum is that all of the galleries are on one single plane. So if you go to a lot of museums, you have galleries on several different floors. You go to floor 2 for European art, you go to floor 4 for like Asian art. And the idea for this museum is that all of these galleries are on the same plane. So there's like sort of an equal access that everyone has to these different types of art. So this led to what you saw, like a very kind of flat, large structure that's, technically speaking, it's only a 2-story building because there's only one floor that is the main exhibition floor. Some more diagrams to show the interaction between the different gallery spaces, and the hierarchy is already starting to form and the pathway between the different galleries. Another shot of Peter Zumthor in his studio and kind of working through the physical models to imagine the space. In 2016 was when we actually went through the initial phase of design development, and this is, it shows the concept that now you'll see it's different in a few slides, but the main concept was forming that there are these clusters of galleries. So the more kind of the white boxes are towers that go from the ground up, and then there are interconnecting galleries, the gray boxes that branch off from the towers, but they don't go to the ground. So there are kind of floating galleries that are being suspended off of the ground. In section, we have the towers floating down, and then there's kind of interstitial spaces between the towers are kind of supported by long-spanning slabs. And already at that point, these slabs had the idea of like, so for example, there's a ground level, and then exhibition level, and then the roof level. So the exhibition and roof level are formed by top and bottom slabs. They end up being 8-inch slabs, and vertical ribs that form kind of like a waffle pattern that's hidden between the two slabs. So vertical ribs that are 4.5 to 9 feet tall. So those interstitial spaces between the slabs become your mechanical plenum and your maintenance access spaces as well. Some early concepts, Peter Zumthor had really liked this kind of organic flowing of meandering galleries, so we tried to kind of take his idea and rationalize it based on real-world kind of patterns that you see. But we still ran into challenges of, how do you make this actually constructible and repeatable? So a few years later, we developed, went back to DD and developed a more rationalized layout of the plan. And you can see the pairing I was talking about a little bit earlier. The tower that goes all the way to the ground are the solid colors, and then these galleries that hang from it are on the side and in section. That's what it would look like. So the main thing that made this possible is to use PT. And we have PT, I'll show you a little bit more about the hierarchy of the PT systems in the building, but one main concept we had very early on is to have PT tendons that link these floating galleries back to the towers. This is kind of showing us stepping through the rationalization. So even now we have an orthogonal grid, but they kind of don't really relate to each other, and we wanted to come up with a consistent plan for the structure. So we tried to impose a rectangular grid. Didn't seem like it. We were trying to like fit a square peg into a round hole situation. So we thought, why don't we do a rhombus grid? Who says that things need to be orthogonal? Why don't we do 60-degree angles? And this gave us the opportunity to use, various, instead of just 2 directions, you can have 3 directions, maybe even a 4th one you can see on this side. So that kind of gave us a good starting point for the structure and for the architecture. So one thing I hadn't mentioned yet is that in this building, the structure is the architecture. Aside from a topping slab and the glass that wraps around the building, there are no other architectural kind of finishes. There's no partition walls, there's no architectural ceiling. The structure is the architecture. So from very early on, we had to work with our architects and our MEP engineers to lay out the systems in the project, figure out where are the holes that the lights will come through, where are the holes where return supply air would feed the system, and lay that out onto our grid. Additionally, we thought it would be really nice to express this the rhomboidal grid or the triangular grid. So we actually had special formwork that was triangle shaped so that when you remove the formwork, you can see the lines that reflect the grids. So this is a rendering, and this is a real picture from a few months ago of the finished product without any art in there. Again, rendering of the space and what it was a few months ago with the glass installed. Show another rendering and where it is a few months ago. So I hadn't visited the site basically since a year ago when I was, in the middle of construction. So this picture is just, for me, mind-blowing. They're currently working on a lot of the site work and then trying to wrap up and start moving in the artwork. So let's talk a little bit about how we made this happen. The post-tensioning system, let's talk through about the hierarchy of the PT. So I mentioned there's PT in the walls that kind of go diagonally through. We also have PT in the vertical ribs. They're allowed to sweep up and down within the slab sandwiches. And then we also have PT in the top slabs to give that additional kind of PT eccentricity. Just to give you an idea of like the plans that we have, this is our PT. They follow the grid directions in both directions. And obviously when the PT is in the slab, you can't sweep it, you can't change the eccentricity very much. So what we did was like have PT that stress from one side and then overlapping with PT that stress from the other side, so that when they overlap in the middle, you get double the amount of PT. So we're trying to control the amount of pre-compression we put in the system by overlapping and tendons and burying dead ends in the slabs. In the rib design, so here you can kind of see a elevation across, let's say like 5 grid lines. There's not too much sweeping up and down here, you'll see, but some of our grid lines are, I don't know, 15 bays long, and then your PT start diving all the way up and down the 9-foot rib. In the walls, we have, like you mentioned before, the diagonal PT that come down, because these walls, they're hanging and they're supporting the floor below. So without the PT, they would experience too much tension. So the PT really helped us with that aspect. Modeling, we managed to find, we tested a bunch of software, did sensitivity analysis, and ended up with the LUCIS software, so the London University Structural Analysis software. And we really liked working with this software because it was able to handle our model, and we were able to model the PT just kind of anywhere we wanted it. There was no constraint of like, the PT must be tied to a certain floor or anything like that. So we really like the freedom of the software. We were also able to use that to account for creep, shrinkage, look at cracking, and all the PT losses from various codes. We were able to check AASHTO and Eurocode and CEB, do some sensitivity analysis using all of these models to come up with our final methodology. We were able to kind of slice the building along our grid lines to integrate forces and do strength checks. And we did, of course, deflection analysis, just some example contours. There's much more math behind it, I promise. Live load deflection and long-term deflection. Long-term deflection especially was very, very important to us because, like I mentioned, there is that glass that wraps all the way around the building. And this glass has your standard, very tight tolerances. So we were looking at 1/4 inch over 10 feet of slope in the long term. And also the top and bottom, the roof sandwich and the exhibition sandwich, they move independently. So because there's different span lengths, there's different loading, those two would move differentially. So we had to ensure that we are working within a certain range of long-term relative deflection that the glass mullions can handle. So we worked very closely with our facade engineers and our contractor to make sure that there are no issues there. We had camber diagrams where we basically very detailed camber points all across the building. One thing that's, something that we don't usually do, but we figured was very important for this project is in our drawings, we actually issued our expected deflections and expected position of the concrete at each stage of construction. So at the top, you have the camber value, and then what do we expect the concrete to be at when the glass comes in? Where do we expect it to be at when the finished floor comes in? Where is it, on the day of opening, which we were projecting a couple years after construction, after the first pour, for example, and then in like 5 years. So obviously there are ranges because we had to put some uncertainty in there, and we had to use language like this is the estimated deflection. We don't know for certain where it will end up, but this is close, very close. So there are some other aspects that I haven't touched on yet. I've talked a lot about the gravity, but since this project is in LA, there is high seismicity. There's so many faults, there's high seismicity, you all know that. So for our building, we actually had horizontal isolation bearing. So I mentioned there are towers that go down to the ground. We have 10 of them, 10 rectangle towers, and each of them have 4 triple friction pendulum bearings under the towers. And these are massive, as you can see. In addition to horizontal movement that the bearings are used for, this building doesn't have any expansion joints. Okay, we had pore strips, we had, pore zones, right, pore sequence horizontally, but there are no joints in the permanent condition, and the whole building moves together. And actually, we were able to, obviously we had to do a shrinkage analysis, but we were able to utilize the horizontal isolators to help mitigate stresses that would be induced during the shrinkage phase. So we studied isolator locking and unlocking sequences to mitigate that. And you can see this is a real picture at one of the isolators of the top of the isolator moving relative to the bottom during the shrinkage phase. Just to kind of illustrate the movements at the 2 ends of the building, and we're looking at like 1.5 inch, looks like, from this specific study. So not too much, but it does help a lot to have those movement. In addition to horizontal seismic, there's vertical seismic. I won't talk too much about it because we're here about long-term deflections. But another consideration we had was that these cantilevers were flapping, in the vertical seismic condition. So we had vertical dampers at the mullion locations to control those movements at the tip. And I'm mentioning that just so that we know that we consider the vertical seismic movement in addition to the long-term gravity movement, and they had to be added together and in consideration with the facade system. So for the last part, now we're just gonna look at some construction sequence and photos. As we said, it's a very long building, so not just the vertical sequence was important, the horizontal sequence was also very important. So vertically, we have kind of what you would expect, build the concrete up to the top and then stress from the top to the bottom. And then horizontally, kind of moving from one end of the building to the other end. And one thing to mention here is that the age of the concrete, we had to consider that carefully because of the combination of the vertical and horizontal sequence. Some of the lower slab of the exhibition level, the formwork was not pulled until a year after it had been poured. And then the PT was not stressed until, a few months after, like several months or more after they were poured. So we had to make sure we consider the age of the concrete correctly in our analysis. And I'll just run through some construction photos to round out the presentation. This is the isolator within the basement. We had to build like a 5-foot moat for the seismic movement. Putting up formwork for the walls. This is the towers that are, poured and stripped. I'm skipping ahead a little bit. Now you can see this is the roof slab being constructed. On the very far end, there's formwork for the ribs. In the middle, there's rebar getting put up. And then there's a portion that's like black formwork. That's the underside. That's the top of the formwork for the underside of the roof slab. A bit closer. And here we have the vertical ribs at the slope roof portion. You have the rebars in, the PT getting threaded through, lots of PT in the walls getting threaded through. Stripping of the roof shoring. You can finally see the length of the cantilever there. Glass getting put in. And then finally, the bottom is also revealed. So that's it for my presentation. Thank you.